Thank you. All right, so if you've seen me before, you know that I understand Russian. I can sort of speak Russian, but I'll do the talk in English because it's just a lot smoother that way. And if you have any questions along the way, feel free to ask. And also, I'll be available afterwards, and we can talk about whatever you want. The microphone in the other room seems very loud. So just to paint a general picture, what we're going to do in the next 45 to 50 minutes or so, we're going to talk about some low-level optimizations, getting stuff out of modern processors that can really make applications faster. Again, if you know me, you know that I like making things faster. This is typically the subject of my conference talks. And for this one specifically, I prepared a bunch of new examples along with some that I visited before, and hopefully this will be interesting for everyone. So roughly what we'll talk about first, I'll spend a few minutes on how modern processors are organized. You might have this picture in your head of what a processor looks like and how it works from, I don't know, 20, 25, 30 years ago, because that's sometimes what they teach in school. And modern processors are a little more complicated than that. We'll see some basic demonstrations of various aspects of CPU architecture as I see it. And then we'll do a deep dive on vectorization, which is something I talked about at one of the previous .nexts, but I had a lot fewer examples, and they were not quite as interesting as what I hope to show you today. So even if you saw a talk on vectorization before, I think there's going to be some pretty cool new stuff. Towards the end, we'll talk about the CPU cache and some aspects of performance that have to do with the cache, and we'll conclude with some scaling bottlenecks and maybe talk briefly about the future of anywhere where I see the future for performance improvement from processors. So this talk is mostly for people who care about pretty low-level performance, getting very high CPU-bound algorithms to work faster. This is interesting in a lot of areas. This is interesting for math, for physics simulation, for games, and even for stuff like databases and searching stuff in memory, things like link if you want, but done efficiently at a large scale. So this is a modern processor, two modern processors really. So on the left, this is just a plain Intel i7. I think this is Skylake, but it might be Broadwell. So it's one of the recent generations of Intel. It's got 4 cores. It's got an integrated graphics card on the chip itself. And I think it's really obvious that the number of cores here is not like super high. And then there's the one on the right, which is an Intel Knights Landing. So, you know, any slide I would be fine with this, but not the one showing you a picture. I really would like the processor to show up. There it is. Okay, so on the right you see a modern Knights Landing processor. This one was released by Intel just a few months ago. It's in the same series as Knights Corner. Has anyone heard of Knights Landing and Knights Corner before? Just a few. So this is a family of processors that used to live on a separate dedicated card. So you'd plug in this card into your computer, and then you'd get this super crazy powerful processor to help with computations. In Knights Landing, which is this recent revision of the architecture, it can run your operating system itself. You don't need to plug this thing into another computer. You can just run your Windows, for example, off this processor. And it has like 70 cores, which is pretty impressive for something you can buy for a few $1,000s. That's what this thing costs, including some onboard memory. It's got 16 gigabytes onboard of pretty fast memory, and of course you can add more memory to the whole box. So it's pretty impressive where we are, how far we are along this evolution of modern processors. And this sort of shows that this whole thing of adding more cores is not dead yet, right? Because it might have seemed like we're pretty much hit the bottom of that. i7 used to have 4 cores 5 years ago, and most i7 processors have 4 cores today as well. And so it's nice to see that Intel is still trying to put more cores into a single package and make it into a general purpose solution that can run, again, the operating system and take advantage of all these cores. So this is what a typical processor looks like. This is one core out of many. It's a schematic, of course, and a lot of processors aren't exactly the same, but Intel has pretty much settled on a similar design for a while, and others are also quite similar. So at the very beginning, there is an instruction cache, which stores recently accessed memory that has instructions inside, instructions the CPU has to run. From the instruction cache, the processor reads into a prefetch buffer. These are just instructions waiting to be executed. Now here's the thing, modern processors don't really execute the assembly instructions you see in Visual Studio when you open the disassembly window. Instead, what Intel has been doing for a very long time is taking these instructions and then sort of decoding them into even smaller, simpler instructions that they call UOPs, micro-ops. So there is a whole set of phases that takes instructions in their raw form, the one you see in Visual Studio, for example, and convert them, decode them into these micro-ops, which are a lot simpler. These micro-ops are then stored in a queue. So there's a queue of micro-ops waiting to be executed, and there's a lot of logic around that as well. There's something called fusion of micro-ops, a bunch of things you can do to optimize the process of executing individual micro-ops. Once you have this set of things you have to do, they get delivered to the reservation station, which is called the back end of the processor, and there we have what's called execution units or execution ports. And there's many of them in each core. So each core is actually capable of executing more than one instruction, more than one micro-op at once. In fact, Skylake, for example, which is Intel's most recent edition of processors, Skylake is capable of doing roughly 4 micro-ops per second if you're good. If you issue just the right mix of things, Skylake can do 4 micro-ops in a single cycle at the same time. From all these execution units, which I'll talk about briefly in a moment, you probably access memory, you read stuff from memory, and you write stuff out to memory. And so there's a series of caches, which we'll talk about towards the end of the talk. There's a series of caches, the L1, the L2, the L3, in a lot of processors, the L4 as well, before you actually hit main memory. So I guess some of it might be familiar, and I just wanted to give you a very quick intro into what a modern processor looks like. And what I want to talk about in a little more detail is this backend, these execution units that live inside the backend of the processor, which are capable of doing multiple things at once. So in Skylake, we have 7 ports in the backend. This is a very rough diagram that sort of shows most things these ports can do, not all. And some ports I didn't have room for, so I just put like a single line. But the interesting ones are obviously ports 0, 1, 6, and 5, because these are the ones I put on the slide. And they can do stuff like arithmetic, adding numbers, multiplying numbers. You have separate kinds of arithmetic. You have floating point and you have integers. We also have vector operations, which we'll talk about a little later. In addition to these, I have colors indicating just how expensive these things are, roughly. So the green stuff is cheap, really cheap. The yellow stuff is not that cheap. And most of the stuff is really in these 2 categories. There are some very infrequent instructions which are really slow to execute, and most of them I haven't shown here, but there's one example, for example, in port 5, you have PCL mul, which is multiply with carry, and this is a pretty slow instruction. There's some other slow instructions, but most of them are pretty quick or somewhere down the middle. Interesting things you can see here is that, for example, if I have a workload where I'm adding a lot of ints, and there are some problems where you just end up adding a lot of ints together, you can keep multiple ports working at the same time if you have the right mix of instructions. If you put the right mix of instructions into the backend, you'll have multiple instructions executing at the same time. And so, like I said, the Skylake backend specifically can do about 4 ops per cycle if you keep putting in the right mix of instructions. And this is pretty important, because this is just one core, and you have many of these cores, and in each core you also have vector units, And of course, you can have multiple processors, each having multiple cores. So there's a lot of stuff that can be going on in parallel in your CPU. This is important to understand. Alrighty then, how do you categorize what's happening inside the processor? How do you fix performance issues? We're going to see a few examples of improving performance. And Intel have this general process called the top-down approach, which really is a very simple flowchart. There's just 2 stages in the flowchart. So in the first stage, you ask, has there been a new micro-op scheduled for execution? Is a new micro-op starting to execute right now? So there's 2 options, either yes or no. If yes, if you're starting to execute a new micro-op, then it could have happened as a result of 2 things. Either you finished an existing micro-op and it executed successfully. This is called retirement, right? So when the micro-op finishes, it retires. So that is good. And what you want to do is retire micro-ops. You want to keep executing micro-ops if you can. However, it's also possible that you threw away a micro-op because it didn't end up necessary, essentially. You did stuff with that instruction, but then you figured you don't need it anymore. And this is a result of bad speculation. You thought you would need this instruction to execute, and you started executing it, but then you had to throw it away because, nope, you don't need it, in fact. And modern processors do speculation. Modern processors try to guess what you're going to do next. For example, if you have a branch, they try to predict which way the branch is going to go. And then if they predict wrong, you have to throw away resources. You have to throw away work that you've already done. So that's the first option, that you actually started executing a new instruction. The other option is on the bottom. You did not start executing a new micro-op. And this can be a result of a stall in the back end of the processor or the front end of the processor. So you might have a stall where you simply can't read instructions from memory quickly enough. You remember that you have to read instructions, you have to decode them, so you might not be keeping up with what the processor is doing. You can't read instructions quickly enough. That's a front-end stall. Or you could have a back-end stall where you are reading instructions quickly enough, but your backend can't execute them quickly enough. So for example, you need to write something to memory, or you have to read something from memory, and that takes a long time, and you just have to keep that micro-op in progress. This is a highly general picture, but it pretty much applies to every single example I'm going to show you. We're going to be improving performance here or there in one of these stages of the processor. And it's important to know these terms, because Intel keep using them in all their examples, in all their tools. A lot of people talk using these terms, so that's why I thought it would be interesting to share it with you. So let's start taking a look at some examples. How many of you have seen the super popular question on Stack Overflow? Why is it faster to process a sorted array rather than an unsorted array? How many of you have seen this before? Just a few. Don't be shy. Okay, still just a few. So this is, you see it's got pretty an incredible amount of upvotes. Here is a piece of C++ code that seems very peculiar. For some strange reason, sorting the data miraculously makes the code almost 6 times faster. And here's the example. I wrote it in C# and then I benchmarked it using benchmark.net, of course. And what it basically does, it takes an array, it goes over all the elements, and the ones that are greater than 128, it will sum. The ones that are not, it will just ignore. And then there's 2 loops, essentially. In the first, we're working with a sorted array, and in the second, we're working with an unsorted array. And we're only benchmarking the actual loop, not, the sorting, obviously. And the results actually look like this for a pretty big array. So it's indeed 6 times faster. In fact, it's a little more than 6 times faster to process the sorted array. And this is a classic example of bad speculation, of branch prediction not working well for us. So basically the reason for this, as some of you already know, is that the processor tries to guess whenever there is a branch, whenever there is an if, and we have an if in there, the processor tries to guess which side of the if we're going to take. When the array is not sorted, we might be taking a different branch every time. There's no pattern necessarily, so the processor can't really guess well. It has to guess, and then the guess might fail, and you spend a bunch of time recovering from that failure. However, if the array is sorted, then your branch prediction is going to work pretty well. You're going to predict something, and then it's going to be probably right for a large part of the array until you reach 128, and then it's going to probably be wrong for that part of the array. So you only have like two outcomes at a very defined point in the array, and branch prediction works much better, and you don't have to discard instructions that you started executing and recover from incorrect predictions. And it's a pretty insane difference, right? It's more than 6 times faster just by virtue of that thing that has to do with bad speculation. So this is a simple illustration. I'll have more of processor behavior. Here's another example which when working on it, I sort of expected it to work, and then you'll see why it doesn't. So in this example, we're trying to take advantage of the processor's ability to do multiple things at once, to actually utilize all the ports. And that's something I talked about earlier. So on top, I have a simple loop that calculates the minimum and the maximum of an integer array. And then on the bottom, I tried to be clever. I figured I don't want to keep the CPU busy here. I want to keep the ports better utilized. So I'm going to do like 2 minimums and 2 maximums, and then I'm going to mix them up together at the end. And like you can look at this thing and you can say, well, what is he talking about? It's going to be faster, but you probably also think it can't be much worse, right? I mean, so here's a stupid guy who's trying to optimize stuff, but it can't be much worse, I think. Unfortunately, it is much worse. So the optimized version is slower by some 40%, right, or something like that. And the reason it is slower, unfortunately, is not that my original strategy is wrong. There is some logic to trying to use more parts of the processor more efficiently. But once you look at the actual code for the loop, you see that the optimized version is not quite optimized. There's a bunch of stuff wrong there, and there's 2 that I can mention right now. First, the actual loop is a lot longer, right? So in the non-optimized case, the whole loop fits on 1 column in PowerPoint in pretty big font. In the optimized case, there's a bunch of code in each loop iteration. And Intel processors are optimized for small loops that are smaller than 56 ops. And in the right example, we have a lot more operations per loop iteration. So that's one failure that we're getting in a very early point of the pipeline. But additionally, there's also the stuff I marked in red, which is range checks. When going over the optimized version, you'll notice there's memory accesses, right? I'm doing data at I, over here and over here, over here and over here. And unfortunately, in the optimized, the just-in-time compiler didn't manage to remove these bounce checks. So the code generated here actually checks on every access if I'm still within the array bounds, if I'm not overstepping the size of the array. And these checks are also quite expensive and have branches inside that have to be predicted. So it's just more work, unfortunately, in the optimized case. So in this case, my idea of optimization didn't quite work, and this is also an important lesson to learn. Okay, the third thing I want to tell you when we're discussing just the basics of processor behavior has to do with vector units. So recall that we have vector operations we can do in our processor, which operate on more than one element at a time. We'll come back to those a little later in more detail. And so I'm showing here just another benchmark of min-max. The one on top is the one we just saw previously, just finding the minimum and the maximum in an array. And the one on the bottom is using vector instructions to process elements more quickly. It's essentially different instructions. It's not the same loop anymore. And the results are quite good. So this is 5 times faster on my hardware than the original. So again, I haven't explained yet what these vector units are. Some of you may already know. We'll talk about this later in depth, but there's definitely some value here. There's something to be gained from using better instructions, from using more clever instructions here. And one final aspect I want to briefly touch on before we move to the more interesting examples is parallelization. Obviously, a lot of times you can gain speed from using more than one core. This is also something you can do. We're not going to talk about that almost at all in this presentation, but you can definitely use many cores to speed things up. In this particular example, I did again a simple benchmark using parallel for large enough arrays, and the results aren't bad. So it's like 2.5 times faster using 4 cores to go over the data in parallel. But using vector instructions, we got a better result with just 1 core. So there's definitely something interesting to be said about vector instructions. So we'll talk about those a little later. At this point, I've shown you examples of different aspects of the CPU, and we have several areas I want to talk about in more detail. These have been just sort of introductory examples. So vector instructions first. How many of you have seen my talk last year, just to make sure? Okay, so just a few. We have, I'll talk about this briefly then. We have in modern processors kinds of instructions essentially. The classic instructions, which you probably read in Visual Studio all the time when you open the disassembly window for fun and just start reading, these are the classic instructions that operate on single values, like add 2 floats together, divide a float by another float, find the square root of this double. These are instructions operating on single values. Modern processors, and that's modern as in 20 years ago at least, modern processors have instructions that can operate on multiple values at a time. These are called SIMD, single instruction multiple data. Some examples of these from SSE are instructions operating on 4 floats at a time. So you can take 4 floats, add them to 4 floats in a single instruction. This one here, add PS, that's what it does. The one down here, vmul ps, is an instruction that takes 8 floats and multiplies them by 8 floats to produce 8 results, again in just a single instruction. So there's something interesting here into how modern processors can do more work in a single instruction. There's always the question of, is it going to be faster than just doing 8 times the old instruction or 4 times the old instruction? But there probably is a reason why Intel keeps adding these instructions, right? So we'll talk about performance a little later. What kind of vector instructions do we have in modern processors? So there's a bunch. The obvious ones are the ones you see most often in demos. Add, multiply, do that kind of thing. You can do conversions, and it's surprising how expensive conversions can be. Like you have an array of shorts, and you want to convert that to an array of floats. This is surprisingly expensive. And the vector operations can make that like 4 times faster in some cases. I've actually had to deal with that problem of converting shorts to floats for a project. Some more advanced stuff is cryptography. Like AES encryption has hardware support in instructions that can be vectorized. There's math operations like exponentiation, square root, reciprocal square root, trig operations, a bunch of stuff like that. Really, hundreds of instructions in modern processors that can benefit from vectorization. So how about performance of these vector instructions? Well, there's 2 aspects by which we measure instruction performance. These are latency and throughput. The latency of the instruction is how long it takes from start to finish. Like I start adding 2 integers, how long till I have a result? So if you look at 2 sample instructions, add is an instruction that just adds 2 ints together. It takes 1 cycle to finish. So, you know, in a modern processor that's running at 3 gigahertz, 1 cycle is like 1/3 of a nanosecond. That's pretty quick. And then you also have the PADDD instruction, which adds 4 ints to 4 ints, producing 4 results. That also takes 1 cycle. Not 4 cycles, not 3 cycles, not 2 cycles, still 1 cycle. Then we have throughput. And throughput has to do with the processor's ability to actually do multiple operations at once. So essentially what can happen is I start doing add, and then at the next cycle I start doing another add while the previous one is still running, and then I can do another add while the second one and the first one are still running. And so I could get the result where in a single cycle I have 3 adds completing. In this cycle over here, from here to here, I have 3 adds completing. So that's throughput. And add can do 3 of these per cycle. Add, if you keep doing adds over and over, you can complete 3 of those per cycle, whereas with PADDD, you can only do 2 of those per cycle, but they complete 4 times as much work. So it's still a good deal, even though it's 2 and not 3 per cycle. So the vector instructions are often just as good in terms of performance as the non-vector versions. And vectorization is the #1 thing Intel is trying to tell us for the last 5 years or so that we absolutely have to be doing. A lot of people are doing parallelization. This is standard, last year's news. Vectorization is something not a lot of people are doing, even in libraries that are supposed to be high performance. So I want to show you some examples. There's more examples than I can spend a lot of time on, but if you have any specific questions, please ask. I'll just review them quickly. So the most obvious thing one can do with vectorization, this is the #1 textbook example, is matrix multiplication. And it's not like matrix multiplication is what you do all day. It's just such a key part of a lot of stuff. It's absolutely fundamental to a lot of machine learning algorithms, to image processing, to signal processing. It's just incredibly useful. And so, yep, you can vectorize matrix multiplication because at the very core of matrix multiplication, there is this line over here. C at I plus j, you increment that by A at I times something plus k times B at k times something plus j. That's just the root, the core of the whole thing. And this can be done using vector instructions instead. So instead of multiplying 2 floats and then adding that to another float, you can be multiplying 4 floats, or even 8 floats, or even 16 floats on modern hardware in each loop iteration. And so the version on the bottom, and I'm not going to spend time explaining the API, but this is part of the .NET framework now. The version on the bottom is using vector operations to do the core of that little loop. So this part over here is multiplying 4 or 8 or 16 elements together and adding to 8, 4, 16 elements at a time. The results are not bad. Again, this is just my hardware that has support for up to 8 float instructions, up to 8 float vectors. It's like 5.5 times faster using the vector version than the original scalar one. So it's pretty useful if your machine learning algorithm is now 5.5 times faster because you can multiply matrices a lot faster. So this might seem, like such a corner use case, multiplying matrices, but it seems like Intel is going to add in an upcoming version of their processor just next year or so, an instruction called V4FMADDPS, which has some very complicated semantics. Try to look at this description and see if it reminds you of anything. So what it's doing is it reads a float from some memory location, and then it puts that float 4, 8, or 16 times in a single vector, and then it multiplies that temporary thing by another vector of things and adds that to something and puts the result in something. And then this whole thing is repeated 4 times with different memory locations, different somethings. What does it look like? This does look like the previous loop. This is matrix multiplication. So this is an instruction that is going to be introduced probably solely for the purpose of doing matrix multiplication faster. And it's going to be a lot faster when this is introduced. So Intel really is doing stuff to make these this specific, very specific operation faster in hardware because it is so important. So let's take a look at some other interesting examples. I'm going to skip this for now. This is also very useful in math, in learning, in games. You have a vector. This time I'm saying vector to refer to a physical vector, like a 3D point, right? So I have a vector and I want to normalize it. What does it mean to normalize? I do x times x plus y times y plus z times z, and then I take the square root of the whole thing. That's the norm. And then I divide each component, x, y, and z, by the norm. So the loop is there. And I have a lot of these vectors to normalize. This is a very common operation. So how do we vectorize this? There's this x times x and y times y and z times z over here. And that's what I would like to do in parallel using vector instructions. So to do that, we actually need the x and the y and the z to be vectors, to be multiple values, so we can use vector instructions to operate at them at the same time. So we're essentially moving from an array of structures to a structure of arrays, which is something I'll come back to in the next slide. So the revisited version looks something like this on the slide. You'll notice I don't have a single array of points. Instead, I have an array of x's, and I have an array of y's, and I have an array of z's. So they're separate now. Each coordinate has its own separate array. As a result, I can vectorize more easily and gain more than 4 times speed from doing so. So the vectorized version is more than 4 times faster. Again, these are not like tiny, insignificant wins. These are major wins for actual real-life situations. So here's an even more real-life situation. This is n-body simulation. It's a pretty familiar problem in physics and also in games and simulations. You have particles, like tiny particles or even planets, whatever, and they interact with each other by gravity. So particles have a mass, they have a position, they have velocity, they have acceleration, and you want to simulate what happens when these particles interact. So there's a loop that you have to run, and at the core of the loop there's this. This is something you have to do for each pair of particles. Each pair of particles is affecting each other, so you have to do all this work for each pair. And then you figure out what the forces are, you update all your particles, and you keep running the simulation. So again, it's going to be hard to vectorize because the way our data is organized is an array of structures. An array of structures means I have the first particle, the first physical body, I have its x and y and z, and then I have its velocity, which is again 3-dimensional, and then I have its acceleration, which is 3-dimensional, and then I have the second particle, x, y, and z, velocity, acceleration, and so on. So it's an array of structures, and that's going to be very hard to vectorize. Instead, again, we should reorganize this data as a structure of arrays. So you have multiple arrays, an array for each component. You have an array of x's, and you have an array of y's, and you have an array of z's, and you have an array of velocity x's, and so on. So 9 arrays in this case, plus the mass, so 10 arrays. And then you can vectorize operations on x's, on y's, on z's, and so on. I'm not going to show you benchmarks because I haven't implemented the whole thing yet, but it is roughly 4.5 times faster in the vectorized version, again, on hardware similar to mine. Not on mine because I haven't tested it on mine, but that's the results we should expect. So again, a pretty big win, all on a single core just from vectorization. These are fairly classical problems that have to do with, math and physics and simulations and whatever. I want to show you a couple of examples from a slightly different domain, from databases. So here's a pretty simple thing databases have to do all the time. Substring search. You have a string, you have another string, you want to see if the first string is inside the second string, or the second string is inside the first string. So strstr for C developers out there. So two versions of this that are benchmarked. The first is C# contains. I have a string, I can do contains, the other string gives me a result, pretty simple. The other version is written in C, and I am calling it from C#. So I'm measuring the whole thing, including the interrupt time from C# to C and back. The reason I'm doing this in C is that I don't have in the .NET framework access to the instructions that I need in this case. Not every vector instruction I can access from C#. The key idea here is the following. What the contains version basically does is it runs over the string, and at each index, it tries to see if that other string starts there. So I'm looking for a substring. I'm just checking if it's at the first position, at the second position, at the third position, and so on. Instead, what the vectorized version is doing is it's testing using vector instructions on a large number of elements at the same time if that element is equal to the first character of the substring, and simultaneously if it's equal to the last element of the substring. So I'm trying to find where in my target string, in the big string, where in the big string I have appearances of the first and the last character of my string. And once I find the candidate, once I find the position, then I test. Then I actually check, go over the whole string and verify. But for the candidate search, we use vectorization. And this is a pretty clever idea. I haven't thought about this on my own, don't you worry. And it is incredibly efficient. It is more than 9 times faster, the vector version, than the scalar one. And that includes the interrupt. That includes your C# application talking to a CDLL. The interrupt transition back and forth, it is still 9 times faster to actually do that. Again, this is just a single core. Another thing that's pretty useful in databases, this is what a lot of databases and full text engines are essentially doing, is sorted set intersection. So suppose you have 2 sorted sets of integers. You have 2 sorted arrays of integers, and you want to find all the common elements on the elements that are in both sets. Why would you need that? So suppose you have documents indexed by something. You have documents indexed by search terms, and then you want to search for Obama and Trump. So you have like 2 lists of documents, and because you have the and in there, you have to find the intersection. You have to find all the common documents in both sets. So, you know, there's the obvious implementation, which is just this. You go over both sets. You see which one you have to increment, which index. This is like an interview question, really. And then you dump the results out to an output array. This is pretty fast, but could be made faster. So again, turns out there is an instruction called PCMP ESTRM, which I can access from C if I go through the intrinsics. Again, unfortunately, I could not do this in C#, unlike the other examples I've shown you, because this instruction specifically is not exposed. So what PESTRM does is it takes 2 vectors and finds common elements. You give it 2 sets of characters or sets of bytes, and it finds which elements are in both vectors. So in this case, my data is characters. Characters in C#, characters in .NET are 2 bytes. So I can do operations on sets of 2 bytes. I have a collection of 2-byte elements, another collection of 2-byte elements, and I have an instruction that actually finds the common ones. Once we find the common ones, we can report which ones we found, and then we need to do some logic to advance correctly in both vectors, which is what the rest of the code here is doing. But the really interesting part is this CMP instruction. And this runs pretty quickly. It's, again, like 4 times faster to do the other sorted set intersection using SIMD. This is assuming that the document IDs that we're intersecting are shorts, just 2-byte elements. And that's why I can use this CMP strm and tell it to compare 2-byte elements. If the document's ID were integers, there's something a little more clever that we would have to do, which I'm not going to talk about right now, but we could still use a similar approach. We'd just have to be comparing 4-int elements, and that's a little trickier. So again, the result is 4 times faster, which is pretty nice. By the way, all the benchmarks I'm showing here are on GitHub. I'll have the link for you at the end, and you can reproduce this to verify what I'm saying, because I might be lying, and also, to learn and see examples of what I'm discussing with you. Alrighty then, I think we're all through with vectorization. I hope these examples have been, inspiring. Right? Inspiring is the word I was looking for. Just in terms of how many different problems can be optimized using this very core thing. So what I'm going to talk about briefly now is cache organization, cache structure, and again, some examples of problems that can be improved by understanding the cache a little better. The examples here are going to be a little simpler because we have less time for those. So this is the general cache structure on a typical i5 processor that has 2 cores. No level 4 cache, EDRAM, that kind of thing. And this typical i5 processor with 2 cores has 3 levels of cache before you get to main memory. So I guess there's no need to explain that the purpose of the cache is to speed up accesses to main memory, but it's important to know just how much we speed things up by using the cache. So a typical level 1 cache access on an i5, like say a Skylake, is about 4 cycles. So again, remember we're running at like 2 gigahertz, 4 cycles is like 2 nanoseconds, that's pretty quick. And the level 1 cache is just 32 kilobytes typically. Then we have the level 2 cache, which takes 10 cycles to access, so that's like 5 nanoseconds, a little slower. We could do a lot of vector operations in 5 nanoseconds. And then that cache is like 256 kilobytes typically. And we have L1 and L2 caches on each core. Then we have a shared cache, a level 3 cache, which could be like 4 megabytes, 6 megabytes, even 20 megabytes on some high-end processors. And that takes 40 cycles to access. So that's 20 nanoseconds. We could do a whole lot of vector operations in 20 nanoseconds. And still, all these layers of cache are a lot faster than going to main memory. Main memory is much bigger, but can take upwards of 100 cycles to actually access. So 50, 60, 70, 80 nanoseconds, a very long time from the processor's perspective. So hopefully this isn't new. Now here's a few examples of where understanding these facts about the cache can help. Again, the trivial one is matrix multiplication. It all just comes back to matrix multiplication because all the problems in the world somehow need matrix multiplication at their core. So the first version of this multiplication loop has 3 loops nested I, J, and K. And then inside we have C at I plus J, A at I plus K, B at K plus J, just what we saw previously. The other version has I, then K, then J. So just the loop order has been changed, the K and the J, the K and the J. Otherwise, the code is identical. Like the code at the core of the loop is exactly the same. Now the reorganized version is almost twice as fast. Just reordering the loops makes it almost twice as fast. And that is within level 3 cache. That's without any memory accesses because the total size of all my matrices is 3 megabytes in this benchmark. So the whole thing fits in level 3. The whole thing sits in level 3 after I access it at least once. So the reason for this pretty significant performance difference, even though we're just operating inside level 3, is the order of memory accesses that we're doing. If you look at this first version, when you read this line over here that has B at K times something plus J, well, K here is changing with each iteration, and so we end up accessing B at pretty random points. We keep jumping around in the B matrix here. Whereas in this version, we're going over all three matrices in order. We're going through the matrices in order sequentially. So again, the difference is pretty significant. This is one of the most trivial examples of how reordering your data helps with cache. Here's a less trivial example. This is rotating an image. You have an image, you want to rotate the image. So the original trivial version is just this loop over here. What we're doing here is going over all the y's and all the x's, and then you have like rotated at x plus y is equal to image at y plus x. That's like nothing to it, that's rotating an image. And the second version here is doing the same thing with 4 loops, right? So instead of 2 loops, we now have 4 loops. The 2 inner loops over here, going over by and bx, are essentially working on a tile from the image and moving the whole tile to another place. This tiling optimization again helps with memory accesses, because over here, this y plus x is going over the image sequentially, whereas x plus y over here is going over the image in pretty much random order. So this helps a lot, again, approximately by a factor of 2, when both images are 1024 by 1024 ints. So that's 8 megabytes for both images. That doesn't fit into cache anymore on my box, the one I tested it on. This actually fits into level 4, which I have, doesn't fit into level 3. And still, it's twice as fast to do this optimization with the blocking than not to do it. I want to show you one final example that has to do with cache over here, which has to do with cache invalidation. Not just accessing the cache correctly, but rather what happens when you have multiple processors, multiple cores, competing for the same memory area. So there is a protocol between processors when both processors want to write to a particular memory area. So what typically happens is both processors have that value in their cache. And then one processor wants to say, I want to write to that value. So it has to tell the other processor, forget about this value, I want to write to it, and then it's marked exclusive in one cache and invalid in the other cache. And only then can the original core actually modify it. So this is the MESI protocol. Intel uses it, a lot of others use it, and it's based on pretty complex messages that the CPUs have to send to each other. CPUs or cores, doesn't really matter in this example. So here's where it can manifest. I have over here a set of threads that want to integrate a function together. They want to do a numerical integration, approximate integral of some function. And I have 2 loops here. In the first example, I have multiple threads, and each thread is calculating a result into some location in a shared array, in a single array shared across all threads. In the second loop, I have each thread calculating into its own local variable over here, and then at the end, it writes the result out to that shared array. So again, the operation, the fact I'm integrating something, is entirely unimportant here. What's important is if I'm constantly writing to that shared array, or if I do the write to the shared array only once. And the results are pretty stunning. So when you have just one thread, parallelizing or not, and parallelizing in both ways takes about the same time. When you have 2 threads, then the first function here is just a tiny bit faster when there was just one thread, whereas the second version is almost twice as fast. When you have 4 threads, this first version here becomes slower than when you have 2 threads, and the second version here becomes again almost twice as fast. So the second version is actually capable of parallelizing, and the first is not. And the only reason for this has to do with these invalidations. Essentially, where all the threads are trying to write to that shared array, what happens is that they keep competing for ownership. one core is telling the other core, no, I want to write here, and then the other core says, yeah, okay, you can do that, but I want to write here as well, so let me have ownership of that location. And this ping pong is responsible for the fact we're not able to scale in this example at all. I'm out of time, so I just want to take another 20 seconds to share just one other final example with you, which is incredibly important, and that has to do with memory bottlenecks. A lot of the things I've shown you today, like vectorization, like parallelization, like taking better advantage of how the processor is organized, a lot of these things can lead to your code being incredibly optimized, incredibly fast, in fact so fast that memory cannot keep up with how fast your code is. So like my laptop here has memory bandwidth of 25 gigabytes per second. That's what you can read from my memory. That's as fast as it can go. I was able to take a very simple operation, calculating a dot product, and make it run on just a single core with approximately 23 gigabyte loads per second. So just a single core was pretty easily able, on a real algorithm, to get pretty close to the maximum theoretical memory bandwidth my processor can support. If you have 4 cores, and I have 4 cores, I could also have 22 cores or 72 cores, it's obviously impractical to keep parallelizing if memory is your bottleneck. And in a lot of problems today, memory becomes that bottleneck, unfortunately. And then, vectorizing and parallelizing just stops helping you altogether. And you have to think about how to avoid these memory accesses, how to make sure all my data fits in cache, or how to buy more expensive processors with more expensive memory controllers that have faster and better memory bandwidth. So again, I'm sorry for slightly going over time. I just want to go towards the end. The examples which I've shown you, all the samples, all the benchmark are online. I hope you saw that modern CPUs are sort of complex, but there's a lot of considerations which are understandable if you keep in mind the structure of the CPU, if you keep in mind that you have to keep the CPU busy, if you keep in mind that you have vector instructions, multiple cores, cache hierarchies to think about. A lot of this stuff can be done from C#. I've shown you some C examples, but a lot of this stuff can be done from C#, and this is also excellent news, that we can have the same level of control over our code as C++ developers. So if you have any questions, I'll guess we'll have to do that afterwards. I was very happy to be here. Thank you for listening. Thank you very, very much.